Okay, so the first example on the hypothesis testing concerning the mean is that suppose that 100 high performance tires are made by certain manufacturer, lasted on average 21819 miles, okay, with standard deviation of 1295 miles. Okay, so it means that the mean x bar, it is equal to 21819 miles. Okay, and the standard deviation, okay, is we have 100 high performance tires made, okay, and they check those 100, okay, so it doesn't say that it is the population standard deviation, it is the sample standard deviation. Okay, so 1295 miles is the sample standard deviation with the sample size of 100 tires. Okay, let me re-narrate it. It says that suppose that 100 performance, the 100 high performance tires are made by a certain manufacturer, lasted on average of 21819 miles with a standard deviation of 1295 miles. So it means that this standard deviation is for this sample, n is equal to 100. Okay, for the population, okay, actually it will be given that the population variance or population standard deviation is this thing. Okay, so here it is not given, so it means that it is a sample standard deviation. Okay, you must read the statement very keenly to see whether it is the sample standard deviation or the population standard deviation. Okay, now they say that test the null hypothesis mu is equal to 22,000 miles against the alternative hypothesis mu is less than 22,000 miles at 0.05 level of significance. Okay, so they say that test the null hypothesis, so h naught we will write h naught. Okay, test the null hypothesis mu is equal to 22,000. Okay, so mu is equal to 22,000 miles. Okay, so this is the value of mu naught, actually this is the assumed value. Okay, and h1, the alternative hypothesis, as the mu is less than 22,000 miles. Okay, now this falls into this left side. Okay, one side, and that is left because it is less than 22,000. This is the average that you want to check, actually, and this is the rejection area. So for this, the left, the rejection area will be minus z of alpha. Okay, and they say that test the null hypothesis mu is equal to 22,000 miles against alternative hypothesis mu is less than 22,000 miles at the 0.05 level of significance. It means that alpha is equal to 0.05. So minus z of alpha, it is equal to minus z of 0.05. Okay, and z of 0.05, we know that it is equal to 1.645. okay, it is from the table, actually. Okay, now we will find the test statistics. Okay, test statistics is equal to is to be found. Okay, so test statistics over here, sample size is 100, so n is greater than 30. Okay, and s is given. Okay, so we will go for the c test statistics. Okay, so z is equal to x bar minus mu naught divided by s divided by under the root n. Okay, so x bar is actually this thing, 21819 minus mu naught is the assumed value that we want to check against the x bar, which is equal to 22,000 S is equal to 1295 divided by under the root 100. Okay, so let's calculate it. Okay, so 21819 minus 22,000, it gives us minus 181 divided by 1295 divided by under the root 100. Okay, so this under the root 100 will give us 10. We know that under the root 100 is equal to 10. So let's put the value minus 181 divided by 1295 divided by 10. Okay, so this will move upward, so we will get minus 181 multiplied by 10 divided by 1295. Okay, so let's multiply it with 181. We get minus 1810 divided by 1295. Okay, divided by 1295. So we get minus 1.397. It can be written as it is equivalent to 1.40. Okay, now we have the z value, which is minus 1.40. Okay, and we actually reject null hypothesis if this value is less than the z alpha. Okay, so minus z alpha will be equal to minus 1.645 actually. So we can say that if z is less than minus z alpha, we reject null hypothesis. Okay, now write it. Z alpha, z is equal to minus 1.40, okay, less than minus 1.645. okay, minus 1.40 is actually greater than minus 1.645, so it is not equal to it is not less than this minus z alpha, so we accept the null hypothesis. Okay, in other ways, actually we can say that as it is concerning only this side, the left hand side, okay, so minus z alpha, actually this is the region for minus z alpha. Okay, and the z that we found minus 1.40, okay, this is the critical region, and this critical region starts with minus 1.645, and minus 1.4 actually lies into this region. Okay, so that is why we accept the null hypothesis. It means that the mean average life is 22,000 miles. Okay, so that is what it actually means to us. Okay, so this was the first problem. Now we will proceed to the next problem. Okay, this second example, actually it says that the specification for a certain kind of ribbon call for a mean breaking strength of 185 pounds. It means that the mu or x bar value, actually it is 185 pounds. Okay, we can also write it as mu. Okay, now if 5 pieces randomly selected, okay, if 5 pieces, it means that n is equal to 5, the sample size is 5. Okay, so if 5 pieces randomly selected from different rows, they have breaking strength of 171.6. Okay, we have a statistical data over here now. 171.6, 191.8, 178.3, 184.9, and 189.1. We have these 5 samples selected, and these are the breaking strength. Okay, test the null hypothesis. Okay, null hypothesis is that mu is equal to 185 pounds. Okay, and the alternative hypothesis H1 is that mu is less than 100, and this mean breaking strength is less than 185 pounds. Okay, at the level of significance alpha is equal to 0.05. Okay, now what we actually do is that we find from this test, this samples values, we find the x bar. Okay, this is the assumed value mu naught. Actually, this is not actually x bar, this is the mu naught, the assumed value. Okay, we will find x bar from here. Okay, and we also can find the standard deviation of the sample. Okay, standard deviation of samples is to be found from this data. Okay, we know that x bar is equal to summation of xi divided by n. Okay, for I is equal to 1 up to n. We have here 5 samples, so I is equal to 1 to 5. Summation of I is equal to 1 up to 5 xi divided by 5. Okay, so xi is, x1 is 171.6 plus 191.8 plus 178.3 plus 184.9 plus 189.1 divided by 5. This will give us a mean value. So let's calculate the mean value and then proceed towards the standard deviation. Okay, so the addition actually 171.6 plus 191.8 plus 178.3 plus 184.9 plus 189.1. Okay, this whole addition will give us a value of 915.7 divided by 5. Okay, so we divided by 5. What we get is, we get 183.14. This is the mean value for the sample. Okay, now we want to find the standard deviation. Okay, S is equal to x minus xi actually it is equal to under the root summation of xi minus x bar divided by n. Divided by n minus 1 actually. Okay, so let's calculate this upper value first and then divide it by n minus 1 and then take the square root of it. Okay, so we can write it as divided by n minus 1, or we can say that 5 minus 1 actually. Okay, and xi minus x bar. So the first xi is 171.6 minus 183.14. 183.14 and taking square of it. Okay, then we have 191.8 minus 183.14 whole square plus 178.3 minus 183.14 square plus 184.9 minus 183.14 square plus 189.1 minus 183.14 square divided by 5 minus 1. We can write it as, let's calculate all these. I should do it in the Excel actually. Okay, and I will show you the values. Okay, I will do all the calculations in Excel and I will find the standard deviation of the sample. Okay, so here I am at Excel actually, and I am putting these values. Okay, second one value is 191.8 actually. Okay, the third one is 178.3. okay, the fourth is 184.9. okay, the fifth one is 189.1. sorry 1. okay, now we have these 5 values. Okay, if I want, okay, I can just go to data. Okay, in data I will go to the data analysis. Okay, and then I will go to the descriptive statistics. Okay, and I will go to the input range. The input range, I select this, and these are grouped by rows actually, not columns. Okay, because it is a single column and 5 rows, so it is grouped by rows. Okay, I will select the new output range and I will click here. Okay, and I can select any, okay, any cell and select OK. Okay, okay, it says that what I need summary statistics actually. Okay, and I press OK. Okay, let's just delete it actually. I select this data, go to data analysis. Okay, okay, now here we have mean over here. Okay, this is the standard deviation over here. This is a sample variance, and all the values are just calculated by the system. Okay, but if I want to calculate, okay, let's I say here it is x bar. Okay, so x bar, this I say is equal to average of these 5. Okay, and I press enter, so it gives me the average. Okay, let's highlight it. Okay, this is the average. Now 183.14, here we also got 183.14. okay, now I have the average. I need to find xi minus x bar, so I need to calculate x minus x bar. Okay, it is equal to this minus this, but each time I have to subtract the x bar, so I put actually F4 over here, so it will repeat it. Okay, and I just drag it down. Okay, now I need to square it. Okay, so here it is and I just drag it down. Now I need to find the sum of it. Okay, actually over here I sum it. Okay, now I have the sum of it. Actually I need to divide it by n minus 1. Okay, so it is equal to this divided by n minus 1. So n is equal to 5 over here, so 5 minus 1 is equal to 4. So I just divided by 4, and here we go. I have the sample variance 67.553 and 67.553, exactly same. Okay, now I want, this is the variance. Okay, now I want standard deviation. Okay, and I know that standard deviation is the square root of a variance, so I need just find the square root of this, and here we go. This is the 8.219 8.219,063, exactly same. Okay, so you can also find it like this. Okay, and you can also do it using the calculations, but for the sake of saving time, I did it over this like this. Okay, so I have now a value over here. This value gives us, this is 270.212 divided by 4. So under the root of 67.533, which gives us a value of 8.219. Okay, so this is the sample standard deviation. Now we need to find the statistics. Okay, which is actually the sample size is 5 less than 30, and we also don't have the population variance or population standard deviation. Okay, we can say that n is less than 30 and standard deviation is unknown, so we use t statistic. Okay, so t is equal to x bar minus mu naught divided by s divided by under the root n. Okay, so x bar over here is 183.14 minus the mu naught is 185 pounds. Okay, which is given to us. Okay, s over here is 8.219 divided by under the root 5. Okay, so let's calculate it. What does it give us? Okay, so this subtraction, the upper values, it gives us a value of minus 1.86 divided by 8.219. It can be just written as this will go upward and divided by 8.219. so let's calculate it. Okay, so I multiply it with the under the root of 5 under the root. Okay, so it gives me a value of 2.236 divided by 8.219. Okay, and this is minus, so it will give us a minus value. Okay, so let's divide it by okay, this is the value of under the root 5, actually 2.236. Okay, multiply by minus 1.86 it will give us minus 4.159 divided by 8.219. Okay, so divide minus 4.159 divided by 8.219, so it gives us 0.506 minus 0.506. so t value is equal to minus 0.506. so if the t value is less than t alpha, then reject the null hypothesis actually. So we have found the t value, we need to find the value of t of 0.05. okay, so this value, this is t alpha and n minus 1. okay, because we have a degree of freedom also associated with the t. okay, so we have now t which is minus 0.506. we just need to calculate t of alpha comma n minus 1. so it is t of 0.05 and 4. 5 minus 1 is equal to 4. so I need to see this value in the table, the t table. okay, the t distribution table. okay, so let see this value from the table. okay, okay, here if we see, actually we want it for 0.05, which is this one. okay, this is 0.05 and the degree of freedom associated is 4. so for 4 and t 0.05 it is 2.132. okay, this is the value that we need. so let's write is equal to 2.132. this is the value for the t alpha n minus 1. okay, now as we know that this scenario is actually referring to only the left side actually, because we want to see if mu is less than 185 pounds and mu is equal to 185 pounds. so this left side is of concern, so we find the value of minus t alpha n minus 1. okay, minus t alpha, so it is equal to minus 2.312. this is the value of minus t of 0.05 and 4. okay, and the test statistics, the t value that we found is minus 0.506. so if this value is less than this one, we reject the null hypothesis. so minus 0.506, if it is less than or equal to t of 0.05 and 4, we reject null. so let's see, minus 0.506 minus 2.312, this is actually, as the values are negative, so this is actually a bigger value than this, so it is not less than or equal to, so we accept the null hypothesis. it lies somewhat over here actually, that is why we accept the null hypothesis. okay, so let's do another problem on a single population. okay, hypothesis testing. okay, so we say that suppose that is known from experience that the standard deviation of the weight of 8-ounce package of cookies made by a certain bakery is 0.16 ounce. okay, it means that a bakery that makes like 8-ounce packages of the cookies, actually the standard deviation of that weight actually is 0.16 ounces. okay, So they say that from experience, the standard deviation of the weight of 8 ounce package of cookies made by certain bakery is 0.16. It means that the population variance or population standard deviation is equal to 0.16 ounce. Okay, because it is known from experience, it is not from the samples data, but it is from the experience. Okay, so to check whether the production is under control on a given day, that is to check whether the true average weight of the package is 8 ounce, employees select a random sample of 25 packages. Okay, that took 25 cookies package. It means that the sample size is 25. Okay, and find that their mean weight is 8.091 ounce. Okay, the mean weight is 8.091 ounces. This is the mean for the sample actually. Okay, so since the bakery stands to lose money when the mean weight is greater than 8 and the customer loses out when mean weight is less than 8, test the null hypothesis mu is equal to 8. Okay, so h naught is mu is equal to 8, that the mean weight is 8 ounces, and the alternative hypothesis is that mu is not is equal to 8 ounces. Okay, now we know that the population actually follows the normal distribution. Okay, so it means that the x, okay, the weights that were checked in the 25 samples, it follows the normal distribution. Okay, now this is the case of the two-sided, the two-tailed test. Okay, the two-tailed test, because it is going on both the sides. Okay, on this side as well as on this side, and we know that on the left side it is minus z alpha by 2, and in the positive side, right hand side, it is plus z alpha by 2. These are the critical z values which will be compare with the z statistics that we find over here. Okay, so we have the standard deviation given. Okay, but the sample size is less than 30. Okay, so we will use the z statistics. Okay, z test will be used, z statistics will be used. Okay, why it will be used? Because we have the population standard deviation. Okay, and the population follows normal distribution. Okay, both the cases are met, so we will use the z test or z statistics. Okay, we know that z is equal to x bar minus mu naught divided by standard deviation divided by under the root n. Okay, so in this case x bar is equal to 8.091. this is the x bar. Okay, the mean weight in the 25 samples. Okay, and mu naught is equal to 8 ounces. This is the mu naught, the assumed value of the cookie. Okay, so the z statistics can be found out as x bar is 8.091 minus 8 divided by standard deviation is 0.16 ounces divided by under the root 25. Okay, we know that under the root 25 is equal to 5. Okay, 5 square, so it will be equal to 5. Okay, so let's cut it out. Okay, so 8.9091 minus 8 is equal to 0.091 ounce divided by 0.16 divided by 5. Okay, this will move to this. Okay, so 0.091 multiplied by 5 divided by 0.16. so let's calculate it, that what does it gives us. So we get over here 0.091 multiplied by 5 is equal to 0.455 divided by 0.16. So let's divide it by 0.16. It gives us 2.843. Okay, 2.843. This is the Z value. Okay, now on the other hand, what we need is, we need the absolute value of the Z alpha by 2, because it is concerning both sides. So an absolute value of Z alpha by 2 will work out here. Okay, so now we need to find the value of the absolute value of the Z alpha by 2. Okay, so the alpha level of significance is 0.01. Okay, so Z alpha by 2 is equal to 0.01 divided by 2, which is equal to 0.005. Z of 0.005. Okay, so this value is equal to 2.575 from the Z table actually. Okay, so what we do is, we reject null if the Z value, the absolute Z value actually, is greater than or equal to Z alpha by 2. Okay, so the absolute value of Z is 2.843. Actually, Z alpha by 2 is 2.575. So it is greater than, so it stands true. So we reject null hypothesis, and we can say that the average weight of cookie mu is not equal to 8 ounces. This alternative hypothesis actually stands true. Okay, so here is an exercise problem that we will solve over here. It says that the security department of a factory wants to know whether the true average time required by the night guard to walk his round is 30 minutes. Okay, so 30 minutes is the assumed value over here. Okay, mu naught is 30 minutes. If in a random sample of 32 rounds, okay, it means that n is equal to 32. Okay, and mu naught is equal to 30 minutes. This is the sample size. In a random sample of 32 rounds, the night guard averaged 30.8. So x bar is equal to 30.8 minutes. Okay, with a standard deviation of 1.5 minutes. So it means that we have a sample standard deviation minutes. This is also minutes. Okay, so determine whether this is a sufficient evidence to reject the null hypothesis of mu is equal to 30 minutes in favor of the alternative hypothesis mu is not equal to 30 minutes. Okay, so here h naught is mu is equal to 30 minutes. Okay, so and the alternative hypothesis is that mu is not equal to 30 minutes. Okay, so this is the two-tailed. Okay, n is equal to 32, so n is greater than or equal to 30 condition is followed actually over here, and we have the sample standard deviation, and the population is following the normal distribution. Okay, we will be using the z-test statistics over here. Why? Because n is greater than 30 and x actually it is following the normal distribution. Okay, so the z statistics, it will be equal to x bar minus mu naught divided by s divided by under the root n. Okay, so x bar over here is equal to 30.8 minus mu naught is 30 divided by s is equal to 1.8 minutes divided by under the root n is under the root 32. Okay, so it will be equal to 0.8 divided by 1.8 divided by under the root 32. It will be equal to 0.8 multiplied by under the root 32 divided by 1.8. Let's calculate it. Under the root 32, it will give us a value of 5.656. Okay, so 0.8 multiplied by 5.656 divided by 1.8. Okay, so let's multiply this 5.656 with 0.8. It gives us a value of 4.525 divided by 1.8. so let's divide it by 1.8. Actually, it gives us 2.514. This is the value of z. Okay, now we have z value, but it is two-sided, so we need to find the value of z alpha by 2. Okay, z alpha by 2 is actually concerned over here, and alpha over here is equal to 0.01. Okay, so alpha by 2 is equal to 0.01 divided by 2, which is equal to 0.005. Okay, so z of 0.005 is actually 2.575. Okay, so we have a criteria to reject or accept the null hypothesis. So we must write the criteria and see if this z value is following that criteria or not. Okay, we know that if the absolute value of z is greater than or equal to z alpha by 2, we reject null hypothesis. Okay, so here the absolute value of z, it is equal to 2.514. okay, and z alpha by 2, it is equal to 2.575. okay, so this value is actually less than this. Okay, so this criteria is not followed over here actually, so we accept the null hypothesis. Why we accept? Because the z alpha, z absolute actually is equal to 2.514. it is less than 2.575, so we accept the null hypothesis, and we can say that the average time to round is equal to 30 minutes. This is accepted. This hypothesis is accepted over here. Okay, so in this video actually we will do the hypothesis testing for two population samples. Okay, the samples taken from two populations. It means that we have two samples from two independent populations. Previously, what we did was we did the hypothesis testing for a single population sample. Okay, we took a sample from a single population. Now we will get two samples from two independent populations, and we will check for the means of it, like whether their means are equal or their means have some difference. Okay, so in this case actually the hypothesis testing concerning two sample means. Okay, so we have two samples, okay, and 1 and N2, okay, from population 1 and population 2. Okay, we can say that it is from population 1 and it is from population 2. Okay, these two populations P1 and P2 are independent, which means that they do not share any of the characteristics. Okay, so in this case the hypothesis testing that can be done is, okay, we have like three cases, okay, case 1, case 2 and case 3 are situations. Cases are situations. In the first one, what we say that the H naught, the null hypothesis, is that mu1 is equal to mu2, which means that the mean for the sample 1 is equal to mean of the sample 2. This is the null hypothesis, while the alternative hypothesis is that H1 is less than H2. Okay, it is also called the left tail test. Okay, the second one is that H naught is mu1 is equal to mu2. Okay, and H1 is that H1 is greater than mu1 is greater than mu2. This is mu. Okay, and this is the right tail test. Okay, and the third one is that H naught states that mu1 is equal to mu2, while the alternative hypothesis is that mu1 is not equal to mu2. So this is two sides, a two-tail test. Okay, it can go both ways. It can either go in this way or in this way. Okay, so we have now these three cases, and we will check for all of the three cases independently. We can either have case 1 or case 2 or case 3. Okay, only one at a time. Okay, now we will we know that in the 4 steps actually that we calculate, the second step is to calculate the test statistics. Okay, and based on this test statistics, okay, let me re-narrate it, the 4 steps. Okay, 4 steps of hypothesis testing. The first one is to construct the null and alternative, and we did that in this case. Okay, the second step is to calculate the test statistics. Okay, and construct the or identify the rejection area. The third step is to analyze or compare test statistics with the rejection area, and the fourth one is to make the conclusions. Okay, whether either H naught is true or false. Okay, so these are the 4 steps. I just re-narrated it, just for the sake of understanding the whole process. Okay, so we will use the either T statistics or Z statistics based on the population distribution. Okay, so based on population distribution and variances, the population variance, okay, we use these test statistics. Okay, the first one is Z and the other one is T statistics. Okay, so in Z we have like 2. Okay, the first one is that the population, okay, X belongs to normal distribution. Okay, normal, and it has a mean and standard deviation. Okay, and standard deviation of first sample and second sample are known. the first population and second population, sigma, are known. Okay. The second thing is that n1 and n2 both are greater than or equal to 80. It means 30. It means that we have large samples. Okay. And we have samples standard deviation, which is S1 and S2. We don't have sigma 1 and sigma 2, but we have S1 and S2. But we will still use the Z test because the sample size is large. It is greater than or equal to 30. And we use T statistics when the sample size N1, comma, N2, it is less than 30, okay? And sigma 1 and sigma 2 are unknown. Okay, so in this condition actually we use the T statistics. Now I will define the formulas for each case of Z statistics and T statistics, and then we will do a few example on these test statistics, and we will calculate whether the means are equal or it belongs into the left or right area. Okay, so let's do the formulas and define the formulas and then go for the examples and problems. Okay, so we have certain cases actually. Okay, so the case 1 is when X belongs to normal population and sigma 1 and sigma 2 are known. Then we use Z statistics, okay, and Z here is equal to Z is equal to x1 bar minus x2 bar, okay, and divided by sigma 1 square divided by n1 plus sigma 2 square divided by n2, okay. Sigma 1 square and sigma 2 square are the variances of each population, okay. So this is the formula. This is for two samples, okay, n1 and n2. N1 is sample 1 and n2 is a sample 2, okay. We have two samples. At the same time, when we had like first only one sample, we calculated z is equal to x bar minus mu naught divided by standard deviation divided by under the root n. So this formula actually will be modified to this when we have two samples and the sample the population variances are the population standard deviations are known, okay. Now we have second case, case 2, okay. In this case, population is normal, okay. It means that X belongs to the normal population with mu and standard deviation, okay. But the population variances actually sigma 1 square and sigma 2 square are unknown, okay. When these two are unknown, okay, and the X belongs to normal population, then we use the T statistics, okay. The other thing is that n is less than 30, n1 is less than 30 and n2 is less than 30, okay. So we use the T statistics and it is equal to x1 bar minus x2 bar, just like the above, but the standard deviation over here, it will be replaced by the pooled standard deviation, okay. Where SP is the pooled standard deviation for population 1 and 2, okay. This is the combined pooled standard deviation, okay. And SP square, the variance of pooled variance, it is equal to SP is equal to under the root n1 minus n1 minus 1 actually into s1 square divided by n1 plus n2 minus 2, this is the degree of freedom, and plus n2 minus 1 into s2 square. Okay, and similarly the variance, the pooled variance, it will be equal to n1 minus 1 into s1 square plus n2 minus 1 into s2 square divided by n1 plus n2 minus 2. Okay, so we will use t statistics when x belongs to a normal population. Okay, x is the parameter actually in focus. Okay, the concern parameter like mean or anything. Okay, it belongs to normal population, or the data from which mean is taken, it belongs to the normal population, but the standard deviations are the variances of the population variances. Remember that population variances are unknown. Okay, now we have like a third case over here. Okay, case 3. Okay, in this one actually what we do is we have, the condition is that we have the n1 and n2 greater than 30. The samples are large actually, but still the population variances actually are unknown, and we have only sample variances or standard deviations. The sample standard deviations or variances are given, which is s1 square and s2 square. These are known, but the population variances sigma 1 square and sigma 2 square are unknown. This is the third case. In this case we also use the z statistics, and it is equal to x1 bar minus x2 bar, okay, divided by under the root sigma 1 square, okay, or s1 square divided by n1 plus s2 square divided by n2. Okay, it can happen that we have sigma 1 square and sigma 2 square are known. Okay, and we also have a condition that the sample size is large but these are unknown. So in that case we will replace s1 square by sigma 1 square if sigma 1 square are known. If sigma 1 square are not known and we have only the sample standard deviation, then sigma 1 square will be replaced by the s1 square divided by n1 plus s2 square divided by n2. It is same as the first condition, this one, it is exactly same. Okay, but in this actually we have the standard deviations or the variances of the population given. Okay, so when these are given, even the sample size is small, we go for the z statistics. Okay, and in this one, if these are unknown but still if the sample size is large, we use again the same formula, but the sigma 1 square will be replaced by s1 square and sigma 2 square will be replaced by s2 square. And if the sample is large and sigma 1 square and sigma 2 square are known, then we use the exactly same formula as the case 1. Okay, so these are the, and we have like a fourth case. Okay, and in this the population from which the data is taken is normal. Population is normal. Okay, but the variances of the population are not equal to each other. Okay, in the pooled standard deviation, in this one the sigma 1 square is equal to sigma 2 square but unknown. Okay, that is why we calculate the pooled standard deviation. We calculate the pooled standard deviation when the variances of both the populations, both independent populations, are equal but unknown. Okay, so that is the scenario. And in this case the population is normal but the variances are unknown and unequal. Okay, so then we use the t statistics. Okay, and it is equal to x1 bar minus x2 bar actually divided by under the root s1 square divided by n1 plus s2 square divided by n2. Okay, and the degree of freedom v, okay, it is equal to s1 square divided by n1 plus s2 square divided by n2 whole square divided by s1 square divided by n1 whole square divided by n1 minus 1 plus s2 square divided by n2 whole square divided by n2 minus 1. This is the degree of freedom, and we find the value of t and v. Okay, this is a special case. We will do some special problems on this, and then you will understand the whole procedure of it. Okay, now coming to the problems on these cases and how we actually differentiate each case from other and solve the problem. Okay, so reading the problem actually logically reading the problem and getting the data out of it is very critical in these cases. Okay, you need to understand that which thing is given to us and which thing is missing, and in which case this particular question is fitting. Okay, so then you use that case and calculate the test statistics and then compare it with the z alpha by 2 or whatever we have t alpha by 2 or t alpha, depending on the hypothesis, if it is only one side or two side or two-tailed or single-tailed. Okay, based on that. Okay, when we do the question, you will understand it. Okay, so now let's do the questions on it. Okay, so here is an example. Okay, we have an example. The example states that a software company markets a new computer game with 2 experimental packaging designs. Okay, it means that we have 2 populations. Okay, design 1 is sent to 11 stores and their average sale first month is 52 units. Okay, with sample standard deviation of 12 units. Okay, design 2 is sent to 6 stores. Okay, and their average sales first month is 46 units with sample standard deviation of 10 units. Okay, test at the 1% of level of significance whether the data provides sufficient evidence that concludes that the mean sale per month of the 2 designs are different. Okay, so first we need to construct the null and alternative hypothesis, and it says that test at the 1% level of significance whether the data provide sufficient evidence and conclude that the mean sales per month of the 2 designs are different. So it means that the mu naught actually h naught is that mu1 is equal to mu2. Okay, the mean sales for software 1, which is mu1, is equal to the mean sales per month for software 2. Okay, software package 1 and package 2. Okay, and h1 is that mu1 is not equal to mu2 because it does not state that whether the sales of software package 1 is less than or greater than 2. Okay, so we conclude that this is the two-tailed test. Okay, this is two-tailed test because there are no specifics or no condition are given that cell 1 is greater than cell 2 or cell 2 is less than cell 1 or anything like that. Okay, if that were given, then we would have changed the alternative to mu1 is less than mu2 or mu2 is greater than mu2. mu1 is greater than mu2. Okay, we would have changed that, but it is not given, so we are using here the two-tailed test. Okay, now let's getting into the question and read it. Okay, so design 1 is sent to 11 stores. It means their sample size N1 is 11 stores. Okay, we got the data from 11 stores. Okay, and the first month sales, mean sales, okay, x1 bar is equal to 52 units, and the standard deviation, sample standard deviation is 12 units. Okay, so 52 units is the mean sales and 12 units is the sample standard deviation. Okay, now the second design 2 is sent to 6 stores. It means that the sample size is 6 stores. Okay, we got the data from 6 stores, and the mean sales were 46 units, and the standard deviation is 2 for the sample is 10 units. Okay, now in which category does it fall? Okay, we know that N1 is 11 and N2 is 6. It means that N1 and N2 is less than 30. Okay, and sigma 1 and sigma 2 are also unknown because we are given the sample standard deviation. Okay, so what we do, actually we will go for the t statistics. Okay, t statistics is the, or t test is the thing that we need to do. Okay, we go for the t statistics. Okay, now it says that the populations are independent with equal variances. It means that the sigma 1 square is equal to sigma 2 square but unknown. Okay, so what we do in this condition, we go for the pooled standard deviation. Okay, go for the pooled standard deviation. So what we do is we will calculate the pooled standard deviation. Okay, and then we will find the t statistics, and then we will compare it to, because it is two side, we will compare it to t alpha by 2 and 1 plus n2 minus 2. Okay, and then we will see if the this t value fall in the rejection area or in the acceptance area. Okay, I will continue this example in the next video. Okay, continuing the example, actually what we had was, we have a two-tail test. We have 11 stores, 6 stores over here, the sample size is 11 over here, sample size is 6. It means that it is less than 30, so we will go for the t statistics. Okay, and the population variations are unknown but equal, so we go for the pooled standard deviation. Okay, so let's calculate the pooled standard deviation and the t statistics. Okay, so we know that the t is equal to x1 bar minus x2 bar divided by under the root sp square divided by n1 plus sp square divided by n2. Okay, but sp is unknown, so sp, the pooled standard deviation, actually sp square, it is equal to n1 minus 1 into s1 square plus n2 minus 1 into s2 square divided by n1 plus n2 minus 2. Okay, so now s1 is equal to, we have s1, the variance is 12 units, and s2 is equal to 10 units. Okay, and n1 is 11 stores and n2 is 6 stores. Okay, so now we have all the data, so let's put in there and calculate the sp square. Okay, so n1 minus 1 is 11 minus 1. Okay, into s1 square is 12 square plus 6 minus 1 into s2 square is 10 square divided by n1 plus n2 is 11 plus 6 minus 2. Okay, so 11 minus 1 is 10 into 12 square is I guess 144, I guess, yes, plus 6 minus 1 is 5 multiplied by 10 square is 100 divided by 11 plus 6 is 17 minus 2 is 15. Okay, so let's calculate the sp square. Sp square, let me make these calculations. Okay, let me confirm. The 12 square will give you exactly 144. Okay, multiplied by 10 will give us 1440. Okay, so 440 plus 10 square is 100, multiply by 5 will give us 500 actually. So 500 divided by 15. So let's add both these values actually. Okay, 500 plus 1440, it will give us 1940 divided by 15. Okay, so let's divide it by 15. So what we get 129.33 is equal to SP square. Okay, this is the value of the SP square, the pool variance. Okay, now one thing that we need to do is actually, if I just remember this point, okay, if the population variances are unknown, okay, and the sample size is less than 30, then we actually, and if the the condition is not properly given, then we assume sometimes that sigma 1 square is equal to the population variances are equal but unknown. We get into this condition. Okay, but if the specifics are given, okay, then you don't need to assume it actually. Okay, so sometimes you have to make the question easy for you. Okay, you have to assume few things, like just we have assumed that both the variances are unknown but equal. Okay, and we find the pool variance over here. Now that the pool variance is known actually to us, let us calculate the t statistics. Okay, so x1 bar is given, which is 52, and x2 bar is also given, which is 46 units. So put the values of x1 bar and x2 bar over here. So we get 52 minus 46, okay, divided by under the root of SP square. SP square is 129.33 divided by N1 is 11 plus 129.33 divided by N2. N2 is 6 totes. Okay, so this will give us 52 minus 46. It will give us 6 units. Okay, divided by, let's calculate the each one of this factor. Okay, so 129.33 divided by 11, it gives us 11.75. okay, under the root 11.75 plus, and 129.33 divided by 6, it will give us 21.55. so let's add both these and then make the square root. Okay, plus 11.75 plus 21.55, it will give us 33.305. okay, so taking the under the root, so it will give us 6 divided by 5.77. okay, now when we divide 6 by 5.77, it gives us 1.039. 1.039, okay, is equal to t. So t is 1.039 or 1.04 approximate value. It will become 4 and 9 will disappear. Okay, rounding off. Okay, now we have the t value. Okay, now it is two-sided. Okay, so when we have like this two-sided value, then the critical value of the t, okay, this is equal to, on this side it is equal to minus t alpha by 2 and 1 plus n2 minus 2, and on this positive side it is equal to positive t alpha by 2 and 1 plus n2 minus 2. okay, so t alpha, the significance is equal to 0.01. okay, 1%. 1% is equal to 1 divided by 100. It will give us 0.01. okay, so alpha is 0.01 and alpha by 2 is equal to 0.005. okay, So let's calculate any of these values. Okay, so let's calculate the positive one. Okay, so T alpha by 2 and 1 plus n2 minus 2 is equal to 15. We already calculated it. 11 plus 6 minus 2. Okay, so it is equal to 15, and alpha is equal to 0.01 divided by 2, 15. It will give us T 0.005 and 15. So from T table, let's calculate this value. Okay, for comparison. Okay, so we have the probability is 0.005. Okay, and the degree of freedom is 15. So take it into the 15 and in front of 0.005, this is the exact cross, which gives us a value of 2.947. This is the value that is actually required. Okay, this is the calculated computed value for T of alpha by 2 and 15, or T of 0.005 and 15. This is the value 2.947. So we calculated the value. Okay, so from T table the value is 2.947. Okay, now we will compare this value to the T value that we found, which is equal to 1.04. Okay, and we know that this is the, as it follows normal distribution. Okay, this is the rejection area. The rejection area starts with the critical value, and the critical value is just like we found, it is minus 2.947, and on the positive side it is start from 2.947. This is the rejection area. Okay, this is the acceptance area, or 1 minus alpha. Okay, this is 1 minus alpha. Okay, this is the acceptance area. Now the T value that we found, okay, it is equal to 1.04. Okay, we know that 1.04 falls in somewhere over this area. Okay, 1.04 falls in acceptance area. Okay, which means that null hypothesis is accepted, or mu1 is equal to mu2, or the average sales of both the packages are equal. Okay, so this is how it is actually done. Okay, or we can say that actually the other way around, if the T value, okay, it is greater than or equal to T alpha by 2 and 1 plus n2 minus 2, then we reject the null hypothesis. Okay, so in this case 1.04, it is less than 2.947. Okay, so we accept the null hypothesis. You can do it both ways. Okay, using this graphical one or in this numerical form. Okay, both are fine. Okay, now doing another problem. Actually, it says that, let's start another problem 2 actually. So the statement is that an experiment is performed to determine whether the average nicotine content of one kind of cigarettes is equal to the average nicotine content of the second type of cigarettes. Okay, so we have two samples. Okay, the cigarette 1, two populations, cigarette A and cigarette B. Okay, these are the two populations or two types of cigarettes. Okay, and it says that if n1 is equal to 50 cigarettes. Okay, first sample that is taken from cigarette A population is 50 cigarettes. Okay, we check or we sampled 50 cigarettes, and we found that the average nicotine content is 2.61 milligrams. So x1 bar is equal to 2.61 mg milligram, okay, with a standard deviation of 0.12 milligram, and S1 is 0.12 milligram. This is the for the first sample, okay. The population 2 cigarette B, actually from this population a sample of 40 cigarettes is taken, and 2 is equal to 40 cigarettes, okay, and we found that the average nicotine content for the cigarette B is X2 in this sample is 2.38 milligrams with a standard deviation S2 is equal to 0.14 milligrams. Now we want to find whether both the nicotine we want to find whether both brands actually have same nicotine level at 0.05 level of significance. Okay, it means that alpha is equal to 0.05. Okay, so what we do is actually we first construct the null and alternative hypothesis. So H naught is that mu1 actually it is equal to mu2, and the second is that mu1 is not equal to mu2. So it is a two-tailed test, okay, and X belongs to the normal population, but sigma 1 and sigma 2 are unknown. The variances are unknown of both the population. We have S1 and S2 are known, okay, but the third thing is that the sample size is greater than 30, and 1 and 2 both are greater than 30. So what we do in this condition is we use Z statistics, okay, we use Z statistics because the sample size is greater than 30. We don't have like the variance for the first population, second population, but the sample size is greater than 30, okay. So we will replace the variances of the both population with the variance of the sample. Actually we will use the sample of the variations the sample variance instead of the population variance, okay, but we will use the Z statistics, okay. So let's continue the problem. Okay, so we know that Z is equal to x1 bar minus x2 bar divided by under the root s1 square divided by n1 plus s2 square divided by n2 in this condition, okay. So now we have the Z, we will find the Z statistics value and we will compare it to Z alpha by 2, okay. So if Z is greater than or equal to Z alpha by 2, we reject null hypothesis. I will also do this in graphical mode, okay, just to make you understand that what we did, okay. So first we alpha is equal to 0.05, okay. So alpha by 2, actually why we do alpha by 2, because it is double sided, okay. So in that case we do alpha by 2, Z of alpha by 2, okay. So alpha by 2 over here is equal to 0.05 divided by 2. So let's calculate first the Z value and then the Z value from the table, okay. So this alpha by 2 will be give us 0.025. So Z of 0.025 is to be found from the table, okay, and Z value from the this formula. So let's calculate the Z value, okay. The Z statistics is equal to x1 bar minus x2 bar divided by under the root s1 square divided by n1 plus s2 square divided by n2. So x1 over here is equal to the nicotine content for the sample 1. Okay, so let's see the question. Actually, the nicotine content for sample 1 is 2.61 and nicotine content for sample 2 is 2.38. Okay, so 2.61 minus 2.38, 2.61 minus 2.38 divided by under the root s1 square. The variance for the sample 1 was 0.12 and sample 2 is 0.14. This is the standard deviation. Okay, 0.12 and 0.14. So 0.12 whole square divided by n1. Sample size was 50, I guess. Okay, plus 0.14 whole square divided by 40. Okay, so let's calculate the statistics. Okay, so 2.61 minus 2.38, it will give us a value of 0.23 as numerator. Okay, now we want to find the denominator value. So 0.12 when multiplied by 0.12, it will 0.12 square, it will give us, I guess, 1.44, 0.01. Okay, this will give us 0.0144. Okay, divided by 50 plus, let's calculate the square for 0.14. So 0.14 squared is equal to 0.0196 divided by 40. Let me confirm the sample size. Okay, n1 and n2. So the sample size is 50 and 40. Okay, so let's calculate this term and add it to this term. Okay, so we have the value 0.0196. so when it is divided by 40, it gives us 0.00049. Okay, so it is 0.23 divided by under the root 0.00049. Okay, let's calculate this value also. Okay, 0.0144 divided by 50, it gives us 0.000288. Okay, so let's add both these. Okay, plus 0.00049, it gives us 0.23 divided by under the root 0.000778. So let's find the under the root of square root of this value. So it will give us 0.23 divided by 0.0279. Okay, so let's divide it. 0.23 divided by 0.0279, we get 8.246. so the z statistics value for this we get is 8.246. now what we want to do is we want to find z of alpha by 2, which is equal to, as alpha is equal to 0.05, so we want to find z of 0.05 divided by 2, so it is 0.25. so from the z table actually we want to find the value of z of 0.025. okay, so let's find it out. Okay, so the value for this z of 0.025 is equal to minus 1.96. okay, so we got the absolute value, so absolute value is equal to 1.96. now if z absolute is greater than or equal to z of alpha by 2 actually, so 8.246 is greater than 1.96. So we reject null hypothesis. Okay, now if I do it in the graphical method, actually this is the rejection area. Okay, this rejection area is somewhat minus 1.96 and 1.96. Okay, so this acceptance area is from 1.9 actually 5 up to 1.95. okay, and beyond on this side and beyond on this side it is rejection area, and the z value that we found is 8.246. so 8.246 might be somewhere over here. 8.246. okay, it might fall somewhere in this addition, which is in the rejection area. This is rejection area, this is also rejection area, this is only the acceptance area, and 8.246 falls in this area actually, beyond 1.96. okay, so that is why we reject the null hypothesis. I hope you have find it useful. Thank you.